ideas you can use for a general problem or a particular scheme which you want to work with. So here I will focus like in more general and give you some ideas. But then these ideas can be extended to your research problem on which you are working with or which you want to work on. So just since we are all numeric analysts and our job is to solve a real life problem. That's the whole idea of generating numerical schemes for solving. So there is a rule for handling any real life problem. I mean, it's just like IFSI. So this I stand for information. Suppose you want to solve an industry problem, then I must have the information about this problem. But for that, the industry persons having better information than us. So we have to talk to him in his language and understand what actually the problem is, what he wants. He is not a mathematician, that is our job. Next is based on the information you have received from the industry person, you have to put in your language. Our language is mathematics. That means we have equations. It could be algebraic, it could be differential, it could be partial differential. So in our case, it could be differential equation. So which, if I say differential equation, that has both PD and OD. So then we will having a mathematical modeling. So next steps, once you have mathematical modeling that involve some differential equations, and then next target, you have a mathematical model that need to be solved. So in general, these mathematical models are very complex, and actually the problems are non-linear, even not linear, and they are coupled. So handling this mathematical modeling is not an easy task. However, we have to be very careful. This mathematical model also based on some assumptions, because this industry person said some information and we may not able to understand everything from him. So we have to interpret in our own way what he said and then have the mathematical modeling. So it has the human error itself. So human error means once we interact with him, we may not be fully understand what exactly he want to convey. But he is very clear what he wants. That is his job. Okay. So he is very clear what exactly he wants from us. So mathematical modeling is a separate area of research where actually they come up with the model problem. And some engineers, they apply this mathematical model to a computer. There are many softwares are available. And this model, once you give an input, so the software, there are many softwares are there, they will give you the output. Outputs are just numbers. Outputs are just numbers. So if we blindly just follow the black box, this software are just nothing a black box. So we don't know what inside is going on there. So if you give an input, there will be always output. That's all. There will be always output. But then with this software, the problem is this output with a number. How do we convince the industry person who is giving the problem this number is correct? So then we may think we'll develop our own scheme. That's called the numerical techniques. So today we are here in the solution process, which is called numerical techniques. So that is the job of a numerical analyst to provide a solution. So here also in the market, there are n number of schemes are available. Many are there. In fact, you might have come across. But this will also generate numbers. If the engineer's black box generate number, then for mathematics also finally output is a number. So then the same problem would come there. How do I convince the person that the numbers are correct? So basically, these two are actually not difficult, the F and S. F is not difficult because based on some idea, based on some laws which we have, saying Newton law, conservation laws, we can have some modeling. And this numerical techniques is actually not a problem. We can give the software, or we can develop some scheme, or we can use some existing scheme and writing our codes. So far, absolutely there is no problem. The problem comes this last I, which stand for interpretation of the result. So here the challenge comes. So as I said, even you use software or you use your own numeric techniques, find difference, whatever, so it will generate numbers. So question is, how do we interpret the solution to the person who has given the problem? If you go with some numbers to him, he may not be happy because he doesn't care about the number. He just want to know whether you are able to solve his problem or not. Okay, so just a minute. Yeah. So he is not interested what you have done. He is more interested whether you are able to solve his problem. So solve problem is what? There is some tolerance level. If you come up with some numbers, he had one idea called tolerance level. So basically, it's nothing but convergence. So that's what we discussed in the morning. The stability and the convergence, he may not understand mathematically, but for layman, it's very easy to understand whether these numbers which generated. But if you see in the morning, to have a convergence, we should have a solution to the mathematical model. Then only I have some sequence xh and exact solution x and then converse. So I should know x. But the whole problem is I do not know the exact solution. If I know the exact solution, then why we have to look for the numerical techniques? So here come a challenge in the interpretation. So what do you mean by convergence if I do not know the exact solution? So there are few ideas which was proposed by mathematicians as well as engineers. So it's like this. The idea is convergence again. When s tends to 0, suppose you take two different step size h1 and s2. Let's say h1 is smaller than s2. Correct? And now you take a difference h1 s2. Now you go to s3. So this error should be at least less compared to if you decrease it, error must be less. So this is one idea. Other ideas are like you can validate your result with the experiment, or if the action data is there. So these are the basically ideas. But actually, this in general, this is tough, and here a lot of mathematics play a role in the interpretation. Basically, some function analysis actually. Yeah. So that's the important point. So this is a more general idea. If we solve a real life problem, actually we're supposed to solve that, but that we should keep in mind. So as I discussed in the morning, same thing. I'll just repeat it because that would be important for my further slides. This is what we have been doing. This is a mathematical model, Lx equal to y. It could be any L could be any operator. Here we are talking differential operator. So basically, in this talk, I will focus on parabolic problem. I will focus on parabolic problem, maybe linear parabolic problem in 2 dimensions. So here, let's say L is this is the operator, which you could see in the parabolic operator. So job is given a y, find x such that this. So this problem doesn't have a exact solution, or it has, but we are not able to find it. So idea is we have to look the solution in some finite dimensional space xh, so that exact problem can be solved by using computer. Mathematically, this is the problem which you want to solve. So morning, if you remember, this xh belongs to where? It is some finite dimensional space xh. But then this xh may not be a subspace of x. So it depends actually. See, basically, you understand why I'm saying this. You should know what you want from the scheme. That's a very, very important point. Okay, you should know what actually you want. So accordingly, you have to design a scheme. So in advance, we should know what I want. So what I want, how do we come to know? That will actually have the physics of the problem. So there are mathematical model which is derived through many conservation laws. So if you have a discrete scheme which is not conservative, then it doesn't make sense, even though you solve whatever you do, because your equation mathematical model have a conservation property, but your discrete problem doesn't have it. So it is not useful. So this XHS should be defined such a way that it should solve the purpose. So as I said, X is not finite dimension space, but X is finite dimension, but it may or may not be subspace of X. If it is subspace of X, then yes, we are in a very happy situation, nothing to worry. But in some cases, this is not subspace of X. Then how do you deal with this? These are difficulties comes once we work with the numerics. Okay. Do you have any questions so far? Because this is a general idea which I thought I'll share with you. Don't hesitate to ask any question. Only thing if they is there, then they will let me know. Okay. Okay. So now come to numerical techniques. So the general approach is, as I told you in the morning, you have a PD or OD. That means you have a mathematical model, define some domain, right? So this domain also sometimes would be crazy. It need not to be bounded. That's another problem. Okay. So things are not easy in general, but what we do for our studies actually is very, very particular cases. Like we take interval, we take a rectangle, etc. But that's very, very particular cases. But in general, things are not easy and very complicated. So you have to discrete a domain somehow. This is known as mass generation, which I told you. So everything depends. How do you generate the mass? So recently, there are many mass generation methods are there for find element methods. Okay, so that you can have a better solution. Then based on this, we have to discretize our given partial differential equation or the mathematical model, which is consist of differential equations, right? So as you have seen, once we apply this discretization, this will give you a algebraic equation. That's the whole idea. You have so what we do in the numerics, you have a OD, you have a PD, some numerical techniques.
Sir, one query still.
Yes, there is a doubt.
Yes, sir. X is a
Yes.
subspace of Y. What that means? Just an example.
Yeah.
Yes, sir.
So, sorry.
X
Yeah.
is a space of Y.
Yeah.
What that?
No. X is just it's not a subspace of X, right?
Yes.
So what do you mean? Like you have seen square integral functions, L2 functions, square integral function, or continuous functions, right? Set of all continuous functions. Have you heard?
Professor Sarvesh, actually one student, his name is Satyendra Prasad. He had asked this question, and whatever you will ask him, he can only write in the chat window.
Okay. Sorry.
Yeah,
I understand.
my student actually interrupted you to let you know the question from the chat box.
I got the idea because this is
Okay,
like
yeah.
Yes.
Yeah. So the question was that X is a subspace of Y. What that means?
Yeah, it means that it should be a subset. A is subset of B means if you take any element in A, it has to be element of B also. A is subset of B, like this, right? That's the meaning of subset. Subspace means you have a vector space structure there. Okay, that's the meaning of subspace. That's all. But now it's not in. No, sorry, I have to say it again. So yeah, that's a good idea if she can read a question. Otherwise, again, I don't know, there's some problem.
Yes, Professor Kumar. She will read the question. Yes, and whenever you are asking anything, the participants who has asked the question, he is replying you in the chat window also. I mean, you can just go to the WebEx platform, then you can see in the chat window that
Okay,
participant
fine.
who has asked
I
the
will do
question.
that.
Yeah.
Sure. Okay. So as I told you, if you have a mathematical model which have PDs, so once we apply a numerical techniques, it will give us linear or non-linear algebraic equations. The point is for each different method, this YH and LH are different, that we have seen. So how do, if you remember in the in the morning Richmond theorem, I have told you this YH, this could be some operator approximation. So for each method, this LH, FH is different. So some well-known schemes which you have come across or you might have heard or you may going to heard, it's like finite element methods, finite difference method, finite volume method, and DG method. But there, of course, there are many methods like boundary element method. There are a few more, or mass-free method. There are many methods are available in the literature. For each method, this LH and FH are different, and this is like a system of solving algebraic equations. And each method, of course, it has own merit and demerit. But finally, as I said, to convince an industry person, I must talk about the convergence. That's the point. Whatever method we apply is regardless of the method, we must have the convergence. This is actually would try, with that we can try to convince the industry person, yes, these numbers are right. That's the only way to convince him. Okay. So for that, if you work in FEM or FDM, we need a very good knowledge of Sobolev spaces. Actually, it's nothing but we need something like function analysis. So sometimes we feel that if we are working in numerics, I don't need anything, only a computer. No, the computer or writing code is not sufficient, is one of the part. Basically, you need good mathematics behind it. That is basically your reanalysis and function analysis. So that only will help you. Yeah. So, yeah, we will go to this for solving equations. I'll just, so we'll focus on our problem is the, as I said, parabolic problem. So here we'll discuss some type of finite difference method, and you might have seen it also. These things you might have seen, maybe 1D parabolic, you might have seen the finite difference method applied and the stability, their consistency, and the convergence. There are two ways to talk about this, either by von Neumann or matrix analysis. Okay, but let's go with the two-dimension parabolic problem. So here I will not go mathematically very deep, otherwise will get bored also. So basically I'll give you some ideas. With that you can understand and what are difficulties. So basically this is the problem. Find U which satisfies this, and here remember my domain is a rectangle here with the A and B side. Okay, this is the problem. So basically it's a heat conduction problem that you might have come. So initially the temperature is not known, and I want to find temperature at any point inside this. So similarly, the temperature at the boundary point also known to me. So this is known as discrete condition. But later I will tell you what are different conditions are there and what are the problem associated with that. It's a simple discrete problem. That means if you have a rectangle, the solution is known on the rectangle also. So in principle, solving this parabolic problem can be interpreted different way. What we do, you solve this Laplacian problem. For each t, now you have a t, you take a different value of t. For each t, you solve a Laplacian problem. Or this, if you don't want discretize del u by del t, it will give you system of coordinate ODE. You can treat this also. This will give you system of ODE. Then you can apply your Rangaputta method, etc. to solve it. This is another way of looking at this problem solving too. Or you can discretize both x, y, and t together, and just it will give you the algebraic equation, and then we can solve by computer. So there are multiple view to solve this. So as you might have seen, you have seen this for solving parabolic problem, explicit method and implicit method. Explicit is what? To reach that level, I just need to see whether just one below level, right? That's what the implicit. You can write the solution in explicit form. Implicit means it is not explicit in the sense, suppose you have a sine xy equal to 0, I cannot write in terms of x. That's the problem. But each one have an advantage, disadvantage. So as I told you, first we have to discretize the domain. So for simplicity here, I have taken the mass size delta x delta, which is actually same. You can choose the same delta x delta y. Okay, so this is my delta x along x-axis and delta y along y-axis. We have m interval here and we have n intervals here. So let's say the point for this x are xi and this is y. Now we shall compute the value of your at t, because the why I start from 1, because at the boundary I know the solution, so I don't have to worry about the boundary nodes, because it's a discrete problem. The value is given there at the boundary nodes. So assume that the value of kth level is known, that is t. Similarly, we can discrete time level also, k delta t. We have to compute the k plus 1 level. That's a job. Okay. So let's go with the explicit method first. So if you have this del u by del t derivative, you have to approximate it. Similarly, this too. So here we apply the central difference scheme for x and y, and forward in time, that become explicit. Okay. So the idea is that k plus 1 minus k, and here this order data is nothing but you can apply a Taylor series also, you get this, right? Yeah. If you apply a Taylor series expansion, we get. So this is what it is. Now, just apply Taylor series expansion, I will get. So now, if I ignore this order of x squared, this becomes an scheme. This becomes an scheme. So neglecting the truncation error. So actually, by writing this itself, there is an advantage here. This you can see the scheme is consistent or not. Because whole idea is that if your when delta t, which is time, and delta x delta y tends to 0, this will test to your ODE. That's the idea. This will test to your ODE. Look at this. If delta t tends to 0, this is actually a partial derivative. That's all. Similarly here, this becomes the second partial derivative and this becomes partial derivative. So what happens? Consistency means what? You have a finite difference scheme. FDE should behave like your PDE. It just like become your PDE when delta t delta. That you can see from here itself. Okay. That you can see from here itself. When delta t tends to 0, delta x tends to 0, delta y tends to 0, this actually becomes your this one. This is the meaning of consistency. Your finite difference scheme becomes your PDE. That's all. So we can rewrite this in this fashion, right? Now you can rewrite this as a matrix form. That's all. This is what we want to write. You can rewrite that into a matrix form. So suppose for simplicity, if I take delta x to delta y, then use this notation r delta t by del x square, I can rewrite the 3 in this fashion, right? Now you can have the matrix form. For you iterate on this, k equal to 0 to 1, etc. You can have the matrix form you have ready. So I can rewrite this as ax equal to b. Now why it is explicit means, look at k plus 1 depend only at k. If you know k, then for example, if I start k equal to 0, that value is known to me, right? So you can get u1 and keep iterating this. That's all. So consistency is straightforward. I will again come back, but this scheme is conditionally stable. Means what? There are two discrete parameters here, delta t and delta x. So conditionally stable means what? We are not free to choose delta t and delta x or delta y. That means there should be some relation holds to get it stable. Of course, if a scheme is not stable, we cannot have the convergence, right? That's the whole point we have to remember. So here just straightforward. This is the discretization, right? So if you do the von Neumann stability analysis, which you have seen looks like, so this you can just do with the G, right? Where G is this, that you might have seen. I believe that. Then condition is that this has to be less than 1. That means this number, if you see, has to be less than 1. That means R has to be less than 1 by 4. So here this scheme is stable provided delta t is less than delta. So this is the relation. Means what? I cannot take delta t as I wish. Delta t has to be delta x square by 4. That means we have to take very, very small step size for delta t, which makes the scheme more expensive. That's one. Consistency is straightforward here because this is what it is. Delta t tends to 0. This one delta t. This is this, right? So it is straightforward. And the truncation which you have seen is nothing but delta t, delta x square, delta y square. So I repeat, the constant is nothing but when delta t, delta x tends to 0, or you can say your local truncation error should tends to 0. Both are same. Your local truncation error should be 0 when this your mass size tends to 0. Let's see the implicit scheme. So now we have this at k plus 1 level, all this. So again, you have k plus 1k, but right hand side you have k plus 1. So again, the local truncation is same order delta t order, because we haven't done anything with that. This is delta x square, right? This is the same scheme. Only thing that I cannot write k plus 1 in terms of k here. That's not possible. That's the implicit. But we'll see the advantage of that. So I can rewrite, neglecting the truncation error, and then I can rewrite this equation this way. Again, just same notation, R is delta t by delta x square. I can write this in a matrix form. This is your matrix structure, right? So now I have to, of course, consistent. That's a straightforward. But whether it's stable or not, that we need to check. Yeah. So unlike this express scheme, the scheme leads to a system of linear equation which must be solved for uk plus 1. So this is the structure we get, right? uk plus 1. The A is here. This is the structure you get. Okay. This is the structure you get. So there are a disadvantage here. This actually is not a tri-diagonal structure. So maybe in the second half of the lecture, you will see why actually we prefer the tri-diagonal structure. If you do not have tri-diagonal structure, then there are several issues would come. But if you have a tri-diagonal structure, then we can apply many techniques which can solve efficiently your algebraic equation. So the problem comes here. It is the we do not have here tri-diagonal structure because it's a pentagon, right? Okay, it's a pentagon. But the advantage is that it is unconditionally stable. So it's like a give and take. We have something, but we are losing something. Understand? So that part we need to see. So this is the discretization, right, with the terms of R. So if you look at this one analysis, this is G, and since this denominator are greater than 1, this will be always less than 1. This will be always less than 1. So it doesn't matter what I choose delta t. That means I can free to choose my delta t. It's not, it doesn't depend on the delta x or delta y. I can freely choose. But the problem is here, I do not have this tri-diagonal structure. That is missing. Why we need it? That you will see little later, actually. Okay. So consistency order is same. So consistency order will reflect in the order of convergence, actually. So convergence is same, but the advantage is we have unconditionally stable. But what we are paying, that it's expensive in the sense we don't have a tri-diagonal structure. So let's see this Craig-Nicholson scheme also, which you might have seen, right? Yeah. So what happens? We have taken k level and k plus 1. Now idea is to take the average of these two. Take the average of these two. That's called the Craig-Nicholson scheme. So I have k plus 1 here, right? So you have to approximate this derivative del 2 by k plus 1, and right hand side this is the operator k plus 1. So here idea is just approximate it k and k plus 1 and take the half. That's what the central scheme schemes. So you have to approximate this derivative and get the system. Let's see. So if you do that, just apply again your Taylor's theorem. I get the same thing, but here you get delta t square, and here you get delta x square, delta y square. That means here the truncation order would be delta t square and delta x square, delta y. Remember, in the implicit and explicit we have only the delta t. So that the big advantage we are achieving is faster. It is faster. So like before, if we neglect this local truncation errors, that means these two terms, then I can rewrite this as this, right? This is this. So now I can rewrite this matrix form and you can solve it. So if you use this notation same, so that means if you take delta equal delta y, which is not necessary, just for simplicity, I can have r is delta t by delta x square. So with this notation again, I can rewrite simpler form and then solve this system. So this will give you the m-1 n-1 equation per time step. So each time step you have here m-1 n-1 equation, right? It would be m by n if you do not have a discrete data. That you will see a little later. It could be more, the dimension will be more of this matrix if you have a Newman condition, which you see later, I mean m by n. Why we have m-1 here? Because at the boundary the solution is known. Coefficient is matrix is sparse, but it's not diagonal. The same problem we have here as a pentagon. Complex course is similar to the implicit scheme. The advantage is unconditionally stable. Okay, this is same. Moreover, this has second order accuracy in both space and time. So that's a big advantage compared to the implicit. I have the advantage here, delta t square. But then again, the same issue persists here. We do not have the tri-diagonal structure. We do not have the tri-diagonal structure. Maybe those who are from mathematics background, they would appreciate if you have a tri-diagonal matrix, how beautiful it is. So, but once we are losing this tri-diagonal structure, actually we are paying a lot. Actually, we are paying a lot. So now question is it possible to get a tri-diagonal structure with this same accuracy? That's the question. So what I want everything now. I want second order accurate. I want unconditional stable, because I should not impose the condition on the time and the space. This should be two independent, let be independent. And then I also want this tri-diagonal structure. So how do I achieve these three? The problem is only here, this is not achieved. Otherwise, a very beautiful scheme. I have everything what I want, but this is missing. So here the idea is you have two operator here, uxx with respect to x, and you have uyy, that is y. So we have to deal these two separately. Don't treat them separate. So like in a class, there are different students. We treat them separately. That's the idea. So don't treat them same. With that, we get the actual tri-diagonal structure. So this is method is known. So let me just discuss the stability also for this method. It's a straightforward, by the way. But since we are discussing others, let it be here also. So this is your discrete scheme, right? This is your discrete scheme. So again, this one Newman stability analysis, this matrix G is which is given by this, right? Of course, G mod of G is less than 1 for all values. This is unconditionally stable. And consistency of or delta t square that we have seen, that means convergence also will be delta t square. So both have the same square convergence. But what we don't have, only a tri-diagonal structure. Can we have it? That's the question. Yes. So that can be done with the alternative direction approach, ADI approach. So this ADI method suggested by Peaceman and Rashford in 1985 is a combination. This is what actually we have. It's a combination of explicit and implicit scheme. The method is unconditionally stable, that you will see, and the method is performed in two stages. First is from k to k plus 1 level, and other one is k1 plus. It's like a multi-step method. This is the same idea what we used in multi-step method, or you can also call it multi-level method actually. So the same idea what we do in a single step method for ODE and multi-step. So reach k plus, I need to reach k plus 2, I need k and k plus 1. So k plus 2 is sub-interval, okay, but I need k plus 1 and k. So this, if you recall, this is my problem which I wanted to solve, right? Delta T. So I will treat these two guys separately. This is delta UXX square, the partial derivative of U and Y separately. So let us do that. So stage 1 is like a practical scheme. Describe the equation is at the point k plus 1, but instead of taking the average of both space derivative, one derivative is approximated by unknown level and another one is approximated known level. So see, look at k and k. These I don't know. Okay, so now you have a Taylor series expansion and approximate derivative like this, right? That we have seen. This is your central difference scheme, etc. Now, if you use the same notation for R1 delta Tx square and R2 delta, I can rewrite this in this fashion. That's what we have done before. Now, stage 2 is advancing k plus 1 to k plus 2 level. So now I have to work on this. Delta is approximate by at k plus 2 level and delta is at k plus 1 level. So that means the direction of this kind of space that is altered. That's why it's called alternate direction method. So here I have this k plus 1, k plus, but this is k plus 2, right? This have k plus 2. Now again apply your Taylor series expansion. We have this, and with the notation R2 and this delta t by delta, I can rewrite in this. So I have 12. So you divide the whole thing in two parts: first stage and second stage. So first stage, that's the equation I get, 12.3. In the second stage, I get 12.4. Now let us try to combine it. So look at, first we have to see the consistency. So consistency is straightforward because this local Tank sandwich tends to 0 as per the Taylor series. Now if you look at the stability, I can rewrite this system in this fashion. AX is the matrix which I have just shown to you, right? The structure and A1. So with this again, I can show that this matrix G, if you compute, with less than or equal to 1 when this is positive. So this could be R1, R2. I thought, okay, it's okay, it's a typo. So this is unconditionally stable. So if you want to have the matrix associated with this, that also possible. So look at, in the first step, we are doing this. This is the equation of first step. This is my second step. So you eliminate this k plus 1 from here and rewrite this as. So this is what happened now. If you, this G from here, this is the matrix. This is the matrix form. So this is the matrix form of ADI scheme. ADI scheme. So you have, so here interval is not like 0, k plus 0, k plus 2, one interval, right? K plus 4, etc. This one. So if you want to do the stability, one is von Neumann, otherwise you can have a matrix form also. So it is straightforward that the eigenvalue of this is always less than 1. Let's see that. Okay. So suppose you have the eigenvalue associated with the operator AX, which is nothing but UXS, right? So then this equation I can write the compact form G phi mu phi. So it is straightforward to show that this is actually your mu. How we do that? By the relation which we have here. With this relation, we can directly prove that this is, we have this. Okay, just a straightforward. Hence this is. So now, since you have Laplace operator UXS, the eigenvalue will be always negative, and therefore this mode of mu will be less than 1. That means spectral radius is less than 1. That's why this unconditionally stable. So let's see the matrix structure which we are interested in actually. So without ADI, this is a structure which you have seen. This is not tridiagonal. Okay, you have pentagon, right? You have 5. Whereas with the ADI scheme, you get this structure, tridiagonal structure. So by doing that, if you see the computational cost, it reduces to order n square per step. You see, it reduces to 1 because you see there are two. It's n minus 1 square. Just n minus 1. This is 1 step, right? So there are two advantages. We have a trigonal structure, and why we are looking at trigonals, I'll tell you a little more about it later. So we could achieve what we want. Okay. Now let us generalize this idea in more details. So here we have only two operator UXX, positive UXX and UYY, and we treat them differently, right? So here, suppose you have more, then same idea can be extended there also. Okay, suppose I'll take this advection diffusion reaction equation, ut, the divergence of AU and divergence of D grad U. So actually this is your advection and this is your diffusion and this is your reaction term. Okay. So if you treat all them in the similar way, that will be very expensive and you may not achieve what actually you want. So idea is you treat this all three operators in a different way. This is different, this is different, can achieve. So I repeat, it depends what you want. Okay. So as I said here, reaction can be very stiff, require implicit method, while advection may be benefit from explicit method. So if you treat them same, it's not going to work. So to get the more idea, so let's understand through a maybe unified way, so that everything can be put under one thing, and wherever we need it, we can do that. Okay. So we focus on the following Cauchy problem. So you have some operator A1 into whatever it is. So my idea is that I have to deal them differently. Suppose here's a linear operator, okay, but it can be non-linear also. Then we have to deal them different way. So idea is that I have to decompose this problem into two parts and treat one is with A1, one is with A2, and so on. Okay. So here, since it's an easy problem, the get solution that's given to me. Okay, this is straightforward. So one splitting, there are different kind of splitting is possible. Okay, so one possible splitting is which is given by Lee and Trotter. So just to write the full equation into two system, du1 by dt equal to au1, du2 by du2. Now you have to treat this a1 a2 differently. So here, if you are solving this, should be with initial condition u1 tn should be sp stand for some initial gas. Here nothing but splitting. Okay, sp is splitting. Similarly this. Okay, how we are working with this, let us understand. So suppose you have to go from tn to tn plus 1 level locally. Then what you do with a1, you have utn go to utn, then take this here and a2 will lift it here. So finally your ut tn plus is my u tn plus. Okay, this is how it works. But then it is one way, you can split in more way. So what the error here, the local error is here order delta t square. Okay, because this commute. So if not commute, then we may have first order. But since the commute here, let's assume that, then you get the order delta t square. Local temperature. So another way is you can have more splitting. Okay, this was Strang and Marmik operator splitting over. So you have three now: du1 by dt, au1, du2 by a2. These three, right? Now this is with this interval. So you divide the whole interval into like this, right? Tn plus half, tn, and tn plus 1t. Now you have to solve this and get your u. So idea is here u1 tn will be u sp-tn, u2 tn will be this which is known and etc. So if you do it local the way I have done earlier, so for a1 you apply this to utn plus 1 and take it here, a2 will go here, utn plus 1, then finally you get u3. So u3 is my n plus 1 is my u, that side, u3 n plus 1. So what the advantage of doing that? See, sorry, this I can tell you maybe. So idea is that this a1 a2 operators are if bounded, then actually you have stability, then you actually have the stability. So here, what about the consistency? Here you get delta tq. So now the consistency which actually reflect in the order of convergence, I can split in more also. I have done 3, you can do in more. So why we don't take a combination of this ODE, A1 and A2 and just try splitting? So more general would be dui by dt A1 ui and A2 ui minus 1, right? And dui plus 1 dt is this. Now you iterate. And get the answer. So suppose we apply this idea to solve a KDV equation, right? This has many applications, but this is non-linear here. It is not linear. It is because you have a term 6u ux is present here. So this is actually not linear. That's a problem. But KDV equation have many applications once you go even one dimension or two dimensions. There are different versions are there of KDV equation. So I have taken a homogeneous equation here, but there are non-homogeneous equations also. You can treat them. So suppose I want to apply the same idea what we have been doing here, and this is my initial condition known to me. Ux0 is this, right? And let's say this is my boundary condition. So here boundary condition again Dirichlet. Okay, boundary condition again here the Dirichlet boundary condition. But if you come Newman, which we are going to discuss next lecture, then we see the difficulty. If you have a Dirichlet problem, it's very easy to work. If you have a Newman, then it's slightly difficult. But there are different type of boundary conditions. That's what the task was given to me to discuss the general boundary conditions. So here, suppose we know the exact solution. We know the exact solution. So the idea of splitting is here. We have to treat these two operators. These are two operators. Of course, this is nonlinear here, but idea is same. To treat them differently. So we will have this equation, right? Ut minus ux, this is what I told you, and ut equal to minus 6. We have to treat them. Okay. So if you apply the iterative scheme, which you just discussed, right? So uixx and this one, right? So we can approximate this triple derivative and this by this scheme. Yeah, this is the scheme which we have, delta u cube, etc. with this, and then we can solve it iteratively, okay? And we can get it. So I think before going to boundary condition, okay, I'll take a break here, maybe 5-minute break. Then now we will move to the boundary condition and their treatment. How do we treat the different boundary conditions? Okay, that's what I will do in the next lecture. Maybe we'll have some 5-minute break. Is it okay? Hello? Can we have a break now? Okay, Satyan Prasad. Yes, I want, but I want permission from the organizer if they are there. Hello, Dr. Rahul. It seems they are not there, so we will meet after 5 minutes, right? Maybe exactly at 5. It's okay? Perfect. So see you at exactly at 5.
Yes, Professor Kumar.
So can we start again?
Yes. Actually, I also have some network issues. So before break, when you were speaking, I was hearing your voice, but my voice was not going to you.
Oh, I see. No
So
issues. Anyway.
yeah, you can start. Here also it's about to rain. Weather is not so good at Rajasthan also.
I see.
Yeah.
So I hope the
You
participants do not have any internet issues, right? I hope so. I don't know.
yeah, I think it is a momentarily actually. It's not for the long hours. It's momentarily.
Yeah.
You can
So
yeah, you can start. I think.
so my slides are there, right? Again, it's visible.
Yes. The slides are visible.
Very good. Thank you so much. Yes. So let me recall actually what we have done. So we have seen for 2D parabolic equations, then implicit scheme, canonical scheme. The problem was we don't have the trigonal structure, whereas they are unconditionally stable. But with ADI, that means you treat these two of a different way, we can have a tridiagonal structure, that the idea which you have followed, and this can be extended if you have more than one operator also. This idea, same idea can be extended. How to treat that operator? So that depends. Again, what you want is very important. That's all. What you want to achieve, that's very important. You should have a goal, what actually you want. So this is what we have discussed. Yeah. So now let's see what are different type of boundary conditions. So it is not necessary that you have to take the Poisson equation or the Laplace equation, whatever equations you have. This such, because our PD will come up with boundary condition if and initial conditions, both are there. If you don't have, like here we don't have time derivative, so I don't have about initial condition. If you have, so it depends which problem you want to solve. See, the problem is if you don't have the boundary condition, then there's no meaning of having unique solution, etc. That will completely lost. So a PD should come with the boundary condition. And those who work in the numerical of PD, if you change the boundary condition, our life will change. It's not very easy just to deal with the boundary condition. It's not that easy. So actually, there are basically four type of boundary condition we come across. That I'm defining on a bounded domain. But if unbounded domain are there, then we have a different type of boundary condition, which is I don't think I will discuss here. So one is that we have just seen now display data. See, if on the boundary we have the boundary, it could, so here can be a rectangle, domain can be anything. So it, suppose I know the solution on the boundary G, then this is not display solution. So for example, you have seen a tabla, right? We have a tabla. So this problem can be interpreted in different way. The problem is, given a F, which is external force, you are just putting a force, find U which satisfies this with U equal to G on the problem. Okay. So this is the famous problem posed by Dirichlet. In fact, you can view this problem another way. Suppose there is no external force, my Laplace is equal to 0. This is nothing but a harmonic function, right? So real problem was find a harmonic function with some given data. This is a difficult problem. You can try yourself. It's a very difficult problem. It's posed by Dirichlet. So, but here the another problem is with the, anyway, I have given such an example where another problem would come. So the problem is this F, which is external force tabla, it cannot be continuous. You can't have a continuous force, right? It should be discrete or the point-wise force, which in the language of physics may be direct delta functions, right? Then what do you mean by U? If F is not a continuous function, then what do you mean by U? So for that, we have to view a different point of view, the Sobolev spaces, which I told you. So you should have the solution some Sobolev spaces. it won't be continuous. There is no meaning of continuity there if f is discontinuous. So u equal to g means what? There is no vibration of tabla in the boundary, right? Boundary, there is no vibration. That's what the meaning of this limit. Newman what? Its derivative is given there, not the u, but the normal derivative of u is given you. Then a Robin condition. You have a combination of your Dirichlet data and Newman data. This is a combination and equal to some h. Okay, equal to some. It could be 0 also. So like Newman data you have seen with h is 0, but you can generalize more. It need not to be 0. Then a mixed condition. So you have what you do? You divide the whole domain into 2 parts. Boundary. Let's say Dirichlet and Newman. So on Dirichlet equal to g is there, and on Newman it is. So this is called mixed boundary condition. So this would come as per demand on the modeling part. So a differential equation or a partial equation will come with the boundary condition. It could be Dirichlet, it could be Newman, it could be Roman, or it could be a mixed. But treatment for each condition is different. We cannot have the same treatment. It's not possible. That's the problem. So as I said, if you have a mathematical problem, we which is coupled, so we can't have an analytical solution. So we'll go with the finite difference method. Why finite difference method? They are very attractive and easy to understand. You would have been doing last 4 or 5 days, right? But then, of course, there are big limitations of finite difference methods that we'll see. There are big limitations of finite difference method, and it's not that for every problem I can apply finite difference method. That's not possible. So it depends which problem you want to solve and whether your finite difference method or different versions are there can be applied or not. So the idea is after applying FDM, we end up with this equation and then finally we have to solve. The another problem is once we apply this finite difference methods, we come up with a very large and sparse matrix. So it's not like 1000 by 1000 matrix. It would be very large, million by million. So solving this is actually not easy. That's what, if it is tridiagonal, understand? If it is tridiagonal structure, then yes, there are different schemes are there to handle a tridiagonal structure. So that's why I told you we always prefer to have a tridiagonal structure. Another issue is, suppose you have a system of equation A is equal to B. Before jumping to solve it, I should make sure that this problem have a unique solution. So how do we do that? If you have a system of linear equation A is equal to B, how do I make sure that it has a unique solution? So it's not possible. We'll see that also. It's not possible to go to rank idea and the inverse is impossible. Then how do we actually know where this problem has a unique solution? So thereby also, if you have a tridiagonal structure, that will help us. Okay. So it's not only in the solution process, it will also help us if you have for showing that the problem have a unique solution. That's the idea. So let's go with the boundary problem. So here, as I said, we have a different boundary condition. So I will do with the help of 2-point boundary condition, but so that you can easily understand it. And the same idea can be extended to higher dimension, that is 2 dimension. But I will restrict now only for 1 dimension, and you get the idea what actually we can do, and the same idea would be in 2 dimensions. But of course, little more expensive that we have. So see, this is the problem. I mean, I'm putting a general way. Y double dash equal to fx y dash when x is in this interval, and here are the conditions. Alpha ya. So you see, it's actually a mixed boundary condition, right? If alpha 1 beta 1 are 0, then we have a Newman condition. If alpha 2, beta 2 both are 0, then we have a Dirichlet condition. So if you take this to 0, then we have a Robin condition. If you take beta 1, beta 2 is 0, beta 1, beta 2, then I have a Robin condition. So all four would depend here on alpha 2, alphas and betas. So this will cover everything. All the conditions which you have just now told can be rewritten in this way. This will have four conditions. So it depends. You put alpha 0 or beta 0, which one is 0. But at the same time, all cannot be 0. All cannot be 0. Only one alpha can be 0 or one beta can, but all cannot be 0. Otherwise, you don't have boundary condition. So before jumping to solve it, we should make sure that this problem have a solution. See, the problem with most of us, without worrying whether our continuous problem is well posed, we always look for a numerical solution. That is not actually meaningful. That actually not meaningful. So, but I agree that it's not easy always that your continuous problem have a unique solution. Okay, because the mathematical model which you have, it would be coupled also, which I told in the beginning. So it's not just like your elliptic equation or parabolic equation. Okay, there are few more and it would be coupled also. But it's not easy to see that where this problem have a unique solution. But if you go little advanced course of yes, that's possible, but not all. But not all. Again, we should have a restriction on f. It's not easy. Okay. So, for example, in this case, if partial derivative of f and respect to y and y dash are continuous here, and they are positive, then this boundary problem have a unique solution. So here life is much easier. There is no issues. So with this condition f, this problem have a unique solution. Now we have to look for the numerical solution for it. So this second half of our talk is devoted to handling general boundary condition. How do we handle that, and what the difficulty would come? So let us take with the Dirichlet and Newman, and we'll see what difference would come here. So let's start with the linear problem first. So I have my f. This f have this particular form, and y double dash px y dash px y equal to. This is my problem. And now y, the solution at a and b are known. That means we have a Dirichlet data. That means we have a Dirichlet data. And the Newman problem would be, you do not know y, but whereas you know its derivative in 2 dimensions, normal derivative. So you have y dash a equal to b. That's the problem. Okay. So basically we have to look how do we deal with these two conditions. That's that we have to see. Once we understand these two, then others just can be an extension. Your Robin boundary condition or mixed boundary condition is just an extension of this. If we understand how to handle Dirichlet data and Newman data, then rest would be just extension, nothing else. Okay, so we can discuss many schemes, but I think here we are focusing only on finite difference methods. So I have decided to talk about finite difference methods. Okay, we'll see what the limitation of finite difference method also. So finite difference method part, you have to replace this derivative by some difference, right? That's all. That's the idea. The same thing which we have been doing recently, the same thing we have to do it here, right? You have to replace this second derivative, first derivative, that's all. That's nothing but you apply Taylor-Series expansion and get the approximation of derivative. So this is what it is, right? So we have to divide the interval AB into some intervals. So x0, x1 I have taken here. For simplicity, I have taken the uniform grid, but it's again depend on the problem. The uniform grid may not work. There are different type of mesh like C-skin mesh. There are so many meshes are there which is used. It's a demand. It's not just I can use any mess. That's not. And let's say this discrete point is given by this, right? The same notation which we have following earlier. Yi at exact solution, Wi is the numerical solution. So this is the error. And finally, our aim, this must tends to 0 as n tends to infinity. That's the idea. Okay. So the same thing which we have discussed about the error. Okay. The same thing. So how do we apply a derivative? That we have to go with the Taylor series. Okay. So if you have a continuous functions, a smooth function, sorry, then this can be approximated by polynomials. So first part is a polynomial, and the red one is your error part. Okay. So basically, Taylor's theorem says that if you have enough smoothness, your function can be approximated by polynomial. But this error term, the problem is with error term is there, we never compute this error. Actually, we cannot compute because this xi would lie between xi to x. We do not know what actually xi is. It's some number which lie between xi. But however, if you see your truncation error, we can always find the upper bound of the error. We can always find the upper bound of the error, provided this quantity is bounded. Provided this quantity is bounded. So now let's take x equal to xi plus 1, right? Then we have this and we have this. So this is the idea of Taylor series. Now we can approximate derivative. So if you subtract this y dash xi, nothing but yi plus 1 minus 2h. So order h square. Similarly, if we add 20 by 27, this is what we get the order h square. The central difference scheme which we have discussed in case of implicit and explicit, right? Remember? But if you just get it from 26, yeah, you can get the derivative here, yi plus y divided by h, but the local error would be of order h only. So if I use this sometime, that would be slow, because in fact this one is order h square, but this will give me only order h. This will give you the slow convergence, correct? So that's the actual derivative idea which we have used in our calculus. So y dash as this. So when xi tends to xi plus 1, this is my derivative. That's all. So this is the equation, right? Our differential equation which we had. Since we have a discrete data, so I don't have to worry about the endpoints. I don't have to worry about the endpoint because already solution known, because we have a discrete problem. That's what. So this idea can also be used in my previous slide when we have parabolic equation ux and uy. The same idea actually used there. Okay, so this y double dash is replaced by this. Okay, y double dash is replaced by this. Y dash is replaced by this. We can't replace it by yi plus my yi by h because we lose the order. To make it order h square, that's why we have to use it. Okay, and this order h square. So finally, we have order h square. So if you remove the truncation, we can write the scheme, the apple solution. That's my scheme now. Okay, this is my scheme now. So w naught, that is the initial point, and end nodes. The initial and end point, I know the solution. That's why I start from 1 to n minus 1. Okay. So now I can rewrite this in a system. Just put I equal to 1 to n minus 1. I equal to 1 is a system. Finally, I can write this a system. Okay. This is my a, x equal to b. Here, x is w. So I have, look at this. I have a tri-diagonal structure here. Okay. That is still we have. And your DIs, the diagonal entries are given by this, and upper entries are UIs and lower entries are this. So that is straightforward. Just if you put from a equal to 1 when you get this a x equal to b. Okay, this is your w and this is my b, the right hand side. Only thing that we need to solve it. So, but before solving, how do I make sure that this actually have a solution? That's what the question which I asked you. Remember? That's the question which I asked. So how do I do that? The idea is, if you can show, since you have a tri-diagonal structure here, This is SDD. That means what? Strictly diagonal dominant matrix means mode of DI is greater than strictly mode of UI, mode of LI than I am through. Because once you have SDD, it is positive definite matrix and therefore it is invertible. Directly I can show. I can't apply this rank idea because n could be very large. N could be very large. Okay. So now, but how do I show that? This is SDD. So we can do with the similar analysis. So let's say P in CAB, P is your continuous function. That means bounded, right? So that means you have this inequality. So if I choose H such that H is less than L by 2, H is less than L by 2, then I can compute my Li. Li are given here, right? Yeah, there. Li and Ui are given here. So you can compute, right? Therefore, this one minus 1 H by 2, if you do some implementation, this is this and this is this. So I can prove that mode of Di is stricter than mode of Li plus mode of Ui. That means I have the SDD. So look at if P is not continuous, so we have no guarantee that this is SDD. So it's also depend what smoothness we have. So the moment we have SDD, this is non-singular and therefore have a unique solution. Okay, and you can solve it by computer. Now let's look at the Newman problem. Newman problem is what? I do not know y. I know its derivative y dash a, etc. Right? So that means I cannot start from 1. I have to start from 0 because y at a is not known to me. That's the idea. So if you recall, the double derivative are approximated by this, and the first derivative are approximated like this. Okay. Since we do not know y0 and yn, we have to start from here 0 to n. Earlier we have 1 to n minus 1. Since we know the boundary nodes, right? So if you start with I equal to 0, which I have to, then look at here. I need y minus 1. So y minus 1 is not meaningful now for us, right? Similarly, if I go up to n, then I have here yn plus 1. So that's the problem. So what is the meaning of these two? That's the problem. I can somehow handle it in different way, like yi plus 1 yi, but then I don't have order h square convergence. To maintain this, I have to have yi minus 1 yn plus 1. So what do you mean by that? And how do you get these quantities? So that's the problem. Once you go with the Newman condition, once you go with the Newman problem, you have the problem with the y minus 1 and yn plus 1. So how do you deal with that? So it is just, you can think of fictitious node, not real, but we can find these quantities yi minus 1. Okay, that we'll see. Yeah, so let us start with this y dash xi plus 1, right? For I equal to 0, my x minus 1, which is a x fictitious node. So for that, I have a fictitious wf, right? Yeah, but wf, which is nothing but x minus 1. How you can find out? We can find out with the help of boundary condition. We have a boundary condition y dash a equal to alpha, and if I use that y, this is nothing but w1 minus wf, fictitious node divided by 2h equal to alpha. So wf can be found with the help of this. I can find wf from it. Similarly, if you go to n, I need xn plus 1 xf, right? Then wf is known. We have to find out this quantity. That can be found on second condition. I have y dash b equal to beta. That is wf minus wn by 2h. So again, I can find out. So this can be solved with the help of the boundary condition, right? That's not a worry here. It is simple here, but once you go with 2 dimensions, things are not very straightforward. Okay, so this is how we can handle. So let's go back to again, because I want to spend some time here. So finally, if we apply finite difference methods, I will get system of algebraic equation. If a linear, we have a linear equation. If it's non-linear, then we'll see it's a non-linear problem. So how do we actually deal with this linear equations? So why I want to discuss this, because after applying finite difference method, you will end up with A equal to B. And our problem is we actually do not understand how do I handle A equal to B. That's a problem. So let's see what issue we'll face with the linear system, right? So for example, here, if we apply the finite difference scheme, I have the linear system. So this is your A, B. So we know that from our algebra, if rank of A equal to this, and then we have a unique solution, but it is almost impossible to get the rank idea, right? It's not possible because our matrix is very large, so we can't go with the rank idea. So there is a special type of matrix which I told you, SDD. Means what? If you have the diagonal entries is greater than to non-diagonal entries, then this have a unique solution always, which is much easier than to find the rank idea. And suppose you have symmetricity also, then you can have a symmetry point definite. That means A transpose equal to A, then X transpose AX is actually is positive, right? Then A is point definitely and hence invertible, so you can have a unique solution. So in fact, if you have a point definite matrix, symmetric, then you can find the actually exact solution by a numerical solution. That method is known as conjugate gain method. So you can get solution as accurate as you want. That's the idea. So there are some well-known schemes which you have seen, like some direct schemes and some iterative scheme. Direct scheme Gauss elimination method. This is actually create a lot of issues. And value decomposition, Gauss method. The iterative method, you have seen Jacobi method, Gauss-Seidel method, and this etc. Gradient and conjugate. These methods are good, but there are iterative methods. Iterative method means what? We have to talk about the convergence, because it's like a sequence. You are generating a sequence. This has to be converged. So question is, like we have seen many methods, Jacobi, Gauss-Seidel, etc. Whether we really converge, what is the condition we have to impose? Yeah. So for large and sparse system, direct method may not be efficient, and we have to use the iterative method. So if you look at this, is what I told you. If you have a PD or let's say OD, and if you apply a finite difference method, our system is very sparse, very sparse. So there I cannot think of applying Gauss elimination method. So if you use the MATLAB, they actually inbuilt by this way only, right? They use Gauss elimination method, which is time consuming and may not be right. So if you should know how to handle your linear system. So iterative method, you can generate many iterative methods, right? So you want to solve this, you can rewrite a fixed point iterative scheme, xk plus 1 equal to xk1, right? This is a fixed point you can do. So for each method, this t is different. For each method, this t is different. So you have to split it, right? You have to split this method A, the matrix A into M and N. So if I do with, let's say M is non-singular, A is equal to B is like this, right? M inverse N. If you, that means this is my T and this is my C. So like we have Jacobi method, Gauss-Seidel method, it depends how do you split them? How do you split them M and N, right? And then we get the iterative schemes. Because for iterative scheme, what we need only this T and C. So for example, if you have Jacobi method, right? This you might have come across xk plus 1. So you have to generate the scheme that is nothing but x1 kk plus 1 is this. In general, this is the scheme which you have seen, correct? So here, my M actually D and N actually L plus U. So basically we have to, sorry, for this T, which is M inverse N and C is M inverse B. So in the Jacobi method, my M is actually D and N is L plus U. So this you might have seen, right? We'll see the problem associated with this. So suppose you have this 3 by 3 system and you want to apply by Jacobi formula like this. So look at x2. This will depend again on x1. Even x3 would all depend on x1. So the problem is here, like earlier we discussed, it's very expensive. Even for x2, I need x1. That should be avoided. That should be avoided. So how we can do this? That is possible by even Gauss-Seidel method. So this is the Gauss-Seidel scheme which you might have seen, right? Escape. And this is the your formula that just to motivate you. So here M is D and N is L plus U. Sorry. Yeah. So idea is here I don't need have a kx1 by so on next level k plus 1 which is known. So the idea is here whatever known to me I will make use of this. You understand? See, this is known I have used here. This is known I have used here. So this is much better approach than the Jacobi method because whatever given to me I can use it. So we can write this in a more general fashion, that is your successive overreaction method, right? W. If you take W is equal to 1, you become Gauss-Seidel method, right? So for some system, so question is, of course, what could be my W? For some system, W has perform better, but for some system, W is less. In general, we take W is less than 2. W less than 2. But what about the convergence? Finally, we have to worry about the convergence because iterative scheme. So let's say a row with the magnitude of largest eigenvalue, this is spectral radius of row. It is the spectral radius of the matrix A, row A, spectral radius. This is nothing but the magnitude of larger eigenvalue. So there are some results to see when this iterative scheme will converge. So this will converge provided rho T is less than 1. But we have to actually directly check with the x equal to b. We have to check with the x equal to b because we want to solve it. That is the intermediate thing we have to bring it. So a sufficient condition for convergence for Jacobi and Gauss-Seidel method is matrix should be A is SDD. So if you have a tridiagonal structure, I can immediately check whether my matrix A is SDD or not, right? So if it is SDD, then it will converge for any initial guess. It will converge for any initial guess. Similarly, Gauss-Seidel iteration converges for any if A is symmetric and point definite. When matrix A is SDD, a sufficient condition for the relaxation is W should be less than 0 to 1 if SDD. Okay, if the matrix is symmetric point definite, then it will converge for. See why I want to stress on this. Sometimes we write a code in computer and run it. Sometimes we may get wrong answer and we keep trying again. So nothing wrong in computer or your code. There is something wrong with the theory itself. There is something wrong with the theory itself that we need to see. So another problem is if you work with a computer, suppose every computer have a memory, right? If you give the number 1 by 3, it may understand different ways, right? The number 1 by 3, it will understand its own ways. So that means there should be some small perturbation, right? But then if I solve it, whether I get drastic change the solution or not, understand? So let us just look at this. So suppose you have this A and this is B. The solution of this system is 1, 2, minus 1 directly. But suppose B1, you slightly change minus 0.61 to 0.60. That's possible in the computer, right? Just example. Then you see the solution will change like this. This is no more close to your 1, 2, minus 1. I have solution 1, 4, minus. So then what is wrong? The problem is this is not a well-posed system. We'll see this is not a well-posed similar. Similarly, if you change this A11 from 3.03 and if you compute a solution, we'll get this. So its solution is very sensitive to the change in the coefficient matrix, right? So these are ill-posed problem for that we should have a different mechanism to solve. I just can't apply like Gauss-Seidel method or Gauss-elimination method and get a solution. That's not possible. So this is called actually ill-conditioned problem. Ill-conditioned problem is actually, it depends on the behavior of A, the condition number of A. If condition number of A is very high, then there are problems. So to bring down the condition number, I have to multiply by another matrix so that I can bring down the condition number. So that's the problem faced by many engineers actually. They come across about this ill-conditioned problem system. Okay. So before solving A equal to B, which is very important from the perspective that after applying finite difference scheme, I will end up with a system of algebraic equations that we have to deal. Right? Yeah. So nothing wrong with the computer, nothing wrong with the programming. The problem with either with A or with the theory, that we have to fix. Because sometimes we say our finite difference method or whatever technique is not working. So we have to work on Ax equal to B actually. Because finally we have to solve Ax equal to B. That's very important. And I told in the morning, there is a separate branch called numerical linear algebra to handle actually Ax equal to B. To handle Ax equal to B. That's very important because I repeat, once we apply finite difference method or any numerical techniques, this A is very large. A is very, very large. And if you go with the realistic problem, there we have a coupled problem. Even we have more than one equation, right? So, and they are coupled. So A is so large, then handling this is not easy. If you use just by computer, it will take time to get the result. This is another. So we have to handle it nicely. Suppose you have a very sparse system. So I don't have to store every zeros there, right? So you have to store it smartly. Then work with. So for numerical analysis, it's not only the finite difference method we have to worry. We have to actually worry. Finally, we have X equal to B. That system we have to worry. So let's see the non-linear problem. So other cases like Robin condition and this, that you can handle in a similar way, I tell you. Right? Just let's go there for a minute. Once we have, yeah. Suppose now what I did, I have taken in one column alpha 2, beta 2 is 0. So you have y and yb, we could solve it. In another column, I have taken alpha 1, beta 1 is 0, pure in Newman I have solved. Now then suppose you have mixed, right? Alpha 1, ya, alpha 2. So for that, you apply one boundary condition and get it, right? You introduce only 150th node. This also you introduce 150th node. So that can be handled, okay? So once you know how to handle Dirichlet and Newman, their combination also we can handle. This is not a worry. Okay, yeah. So yeah, so suppose I have a non-linear case. Y double dash equal to f of x, y dash. F is here non-linear. So following the same idea that it tells us is, I can approximate derivative by this, that is central difference scheme, and y dash is replaced by this. So I have this, right? So if you are dealing with the Dirichlet data, that means solution at the end points are known to me. Then I have to start from 1 to n minus 1. If it is Newman, then again start from 0 to n and introduce the fictitious node and use the boundary condition to find the fictitious node. The same idea I can do here also. There's nothing to worry about. The problem is Dirichlet or Newman. Okay, this is what we have. Now, See what happens for if you start 1 to n minus 1, since this f is non-linear, we'll end up with the non-linear system of equations. So just to have a compact notation, if we say w is this w just a vector and gw is another vector, then gw is known to you, right? w minus alpha is known to me and this is known to me. So now for I equal to 1 to n minus 1, if I just say gi is this, right? Gi is this one, right? This is my no, sorry. So capital GW is like your system of non-linear equation, the system of non-linear equation. Now, how do we solve this? We don't have a linear now, so it's not possible to apply whatever method, either iterative or direct method, not possible. Then we think of applying Newton method, which has its own problems, we'll see. So if you see, now we have a system of non-linear equation, I want to solve it. Means yes. So the idea is, I can rewrite this as wn plus 1 x into vn vector, right? Where this vn can be computed with the help of the Jacobian. See, if you see the Newton method, you need the inverse, right? But I can't compute here inverse. So inverse will be computed with the help of solving this linear equation at time. This can be computed, right? Where J is the Jacobian. J is this Jacob. This is the Newton method for solving non-linear algebraic equations. Here the problem is iterative schemes. So I have to start from n equal to 0. But then, how do I start? How do I iterate it? X0, like in case of linear, I told you, you have a Gauss-Seidel or Jacobi. If your matrix is HDD or was definite matrix, then it converts for any initial guess. You are free to choose any X node, it will work. However, this is not possible here, because it's again the idea comes from fixed point theory. To convergence, X node is not for arbitrary, it will converse. Then question is, how do we fix the X node? So it depends again which difference equation you have worked with. So there are some ideas to what X node should be, so that this sequence which generates should converse. If it won't converse, then it's not meaningful. It's not meaningful. So this is the GI, right? So if you see that, okay, then you can compute this matrix easily because the structure is so nice. I can compute the Jacobian matrix easily because structure is so nice. We have this matrix. But again, computing our derivative would be very difficult. Then another way of avoid the derivative, like we have a, maybe I'll discuss here if it have. Yeah, we have. So in Newton method, we have to compute the derivative, right? But it's fast convergence. To avoid the derivative, you can use the second method, right? If of course, if Pn close to Pn minus 2 is just like a derivative, which you use the Newton method. So, as I said, you are working with a nonlinear problem. After applying finite difference method, I end up with a nonlinear algebraic equations. How do we solve that? The first problem comes there. It is the initial guess. So this Newton method is actually required very good initial guess. Otherwise, it won't converse. For example, here is the example. If I take this function fx 10 pi x minus 6, I want to find the root of this, right? So I know the exact root is 0.45. Okay, 0.45. If I take p naught, which is actually very close to p, 0.48, p5 will converse. Okay, then p5 will 0.5. After 5 iteration, actually we get the solution. But if I just take p naught 0.4 only, that's a difference, you see, which is again you would say is close to p, but even after 5,000 iteration, it won't converse to p, even after 5,000 iteration. So the big worry is once we deal with the nonlinear equations, the initial guess has to be chosen properly. To come over this, it depends which problem you are solving. So they have the clue. You use that initial guess and then work with it. So blindly, just we can't apply the Newton method and solve it, or Broaden method, whatever it is, it's not possible. So Broaden method is nothing but is the extension of second method in 2 dimensions. That's all. So here, so this is known as the. So we don't have to compute this derivative, which is required for Jacobian. I can do with the help of the second method, which is known as Broaden method. So, but the problem is same. What about the convergence? Okay, so before concluding this, let me tell you the limitation of finite difference methods, which I have not stated here, because so far we are talking about finite difference method, and in the end, if I write so many limitations, then it's not good. Okay, so it has its own advantage. Advantage is what? We can easily understand it and easily have a matrix structure and solve the problem. Then what are the limitations? So if you see, how do we apply finite difference method? So you have to discretize domain first. Suppose you have interval. Already you have discretized, right? In some points. And at each point you can find a solution. Suppose later on, I decided I don't want to find solution at this point. I want a nearby point. It's not possible. So again, you have to refine the mesh to get the solution at this point. It's not possible the way finite difference schemes, because you have a discrete points. So this will give you the solution at the mesh point, no other points. So if you want the solution at other point, again you have to refine your mesh and then get the solution. This is the first problem. Second problem is that we have seen handling of boundary conditions. So the big issue with the finite difference method is handling boundary conditions. The way you have seen is the simplest case, that's in 1 dimension. But if you go to higher dimension, then it's not easy. You have to deal in different way. Okay. The second problem would come. Third, if your domain is complicated, it's very complex geometry. Suppose you have rectangle. Okay, perfect. So if you see, you can have rectangular grid there, right? You can have only rectangular grid, is what we have seen, and then work with this. However, that means they are structure grid. If we don't have a structure grid, which is demand of the many domain, it depends what a domain is, then finite difference method won't work there. Another problem is, with the morning somebody asked me about the smoothness of a solution. So for the convergence in the finite difference method, I need very smooth solution. That's a problem. I need very smooth solution. If solution is not smooth, then I cannot have the convergence. I cannot have the convergence. Similarly, if you come across this similarly patterned problem, where smoothness is issue, I cannot generate the higher order schemes, finite difference schemes. There are problem with that, right? Whereas this all the issues can be handled by finite element methods. So, which is a numerical techniques which handle both PD as well as ODs. The best part is it can handle any boundary condition. It can have any boundary condition, and you have a known structure grid, a triangle. There are, you can have actually polygon masses, which is the latest one, but we can have. The idea is here, you don't, suppose you want to find a solution at some point, you don't have to again regenerate the mesh. With that mesh, using interpolant, I can do that. That's the idea. Because finite element method works on basis function. Finite dimension space, you have a basis function. With that, I can do that. Okay. So this is mostly, of course, this is designed by engineers, but now used by mathematicians with the, and there are different variant of the finite element methods. Yeah. So as I said, this provide greater flexibility to model of complex geometries where FDM fails. can handle any general boundary condition. It doesn't matter what condition you have, we can handle it. Variable material properties can also be handled. This has a clear structure and versatile steps to construct general purpose of software for inferences, right? So this has very strong theoretical foundation. So once we go from FDM to FEM, the stability actually is straightforward. Stability is actually forward, where we have struggled with the in FDM, we struggle a lot. But once you go with the FEM, these things are straightforward, and we have a nice structure for the estimate also. Remember morning I discussed the operator IH and IH, which is very easy to construct in terms of FEM. Okay. Another issue is like singularity pattern problem. So there, if you go with FTM, your uniform mass will not work. You have to go with skin mass, and you have to have more other mass. However, in final method, yes, we can work with any mass. Only thing that we have to add a stabilizer there, and it works well with the singularly pattern problem also. So there are some advantage with the FEM, but the problem is the theory. We have to understand the theoretical behind it. Okay. So that's all I want to convey for this general boundary conditions idea. Okay, thank you so much.
Thank you very much, Professor Sarvesh. It was indeed a very nice lecture, and the way you try to explain each and every part of your lecture, that is really appreciable. Time for some question answers or discussion. Participants, if you have any question, please write in the chat
now
window.
we have time also. Yeah.
Yeah. Anyone if would like to ask any question, I'll wait for 2-3 minutes so that they can write in the chat box. In between, the participants are appreciating the lecture. They are writing. One of the participant, RK Brinda, she's writing, "Thank you, sir, for the insightful talk, both in computation and theoretical area." Dr. Nikhil Srivastava is also conveying thank you. Dr. Atul Kumar Srivastava saying thank you, sir. And RK Brinda, she has asked about 5:30. She has asked a question, tri-diagonal matrix algorithm. She was asking something about tri-diagonal matrix algorithm.
Yeah. So tri-diagonal structure is like I told you, we have a 2-dimension this parabolic problem, right? If you apply the implicit method or canonical scheme, we won't have the tri-diagonal structure. We have penta, right? There are 5 non-zero elements are there, right? So once you have a tri-diagonal structure, then there are very efficient schemes are there to solve the linear system. Moreover, we can easily check whether this is SDD or not. If it is SDD, that means this problem have a unique solution.
Yes, yeah. Thank you. And another participant, Shanti Das, also conveying thank you. The same.
Yeah, again, Thomas algorithm. Yeah, this is what I want to tell you. Yeah.
Yeah, about Thomas algorithm.
You can use Thomas with the tri-diagonal structure. Yeah, but I thought you are not aware. That's why I don't want to bring some name. Yes, you are right.
Yeah, it means our participants are also have very good information about all the algorithms. They are very sincere. They have good knowledge.
Yeah, that's good.
Yeah.
So I just want to convey some idea about numerics, what we do actually, and where we could fail also. That also we have to understand. We have limitations. It's not that I can solve any problem. We have our own limitations. Yeah.
One more participant, Satyendra Prasad, is writing, if possible, codes based on this theory, maybe by old.
Yes. So that actually, if you see standard textbook on, numerical analysis, this is there, right? Yeah.
So he's asking just for practice and understanding some papers with course. Some
Yeah,
old
you
papers.
just take any paper on this finite difference scheme, so it's there. Many papers are there. Or if you want one, I can send you. No issues.
Any other question by any participant?
Yeah, please feel free to ask. I may not be able to answer all the questions, but I will try.
Yeah, the efforts which Professor Sarvesh has put in his lecture, that is really commendable, very appreciable. I have seen that he was trying to clear each and every point with very keen interest. So in future also, if participant have any question, any doubt, they may also directly
Can
write
I
to.
say something about IAST, just 2 minutes?
Yes. We would like to know that. That's so good. Yeah, please tell.
Yeah, I will tell you. So actually, IST, we have now 4 programs. So yes, please, I am going to tell you. So recently we have introduced the postdoc program, and with very reasonable good fellowship, that is Institute Fellowship. You don't need to go with the NPDF or other fellowship directly. You can apply here. You will get very good regional fellowship if you come here for postdoc. Another possibility is we have a PhD program. So without gate also, we try to give fellowship. Okay, and if you have CSR, of course, you'll get the fellowship. But we will cover mostly our research is based on space science. So the idea is once you do a research here, there is scope to work in ISRO because our institute comes under the umbrella of ISRO, right? So here there are fair chances to you get involved in ISRO or some project. Okay. Another possibility is we have this MTech in machine learning and computing. So there we actually take mathematician there, but of course, if you have BTech also, yes, they are welcome, but mostly we focus on good mathematics student there, those who are good in mathematics. So about this program MTech, we have 100% placement. Yes, you can apply actually for MTech, BTech in CSE. Yes, you can, definitely you can. So you can see it's a 100% placement we have so far. You will get the same fellowship what you get 90s, etc. But we can guarantee the placement, 100% placement for this MTech program. Yeah, 100% placement. So basically, we have another way is I told you 4. One way is getting your internship here. If you are looking for internship, which would provide you a platform to see ISRO projects, what actually they work for. That is also one possibility. You can come here for a short period of time and work on some problem which you like, which have some relation with the ISRO projects. That's what, because our main aim to support ISRO actually, technically. Okay. So these are 4 possible ways you can come here and enjoy. And if you need any help, you please drop me an email. I would be happy to respond and try to help you in the way I can. Okay, thank you so much. And I was happy, but I couldn't see you, and that's okay. We'll meet sometime later. No problem.
Yeah, thank you, Professor Sarvesh.
Thank you so much.
Yeah,
And thank you so much, Rahul, Dr. Rahul and Professor Vikas for your impression. Actually, I was very happy to talk about this Lex because he recently passed away. So I was reading about him. Oh, he has done what a contribution. Seriously, I mean, I was really happy to speak on his part. Thank you so much. That's the opportunity I have. Thank you so much.
Yeah, thank you, Professor Sarvesh. And regarding postdoctoral fellowship at your institute,
Yes.
IISST, you have those fellowships in all the departments?
Yes, we have all department, and it's the quarterly based. So after 3 months there is a call. So
Okay.
for that one can refer to our IST page. We have all the departments. Yes.
You have all the departments. So
Yes, we have all departments.
you have all science and all engineering
Yeah, we have earth science, physics, chemistry, maths, whatever possible, yes, we have everything. We have.
Okay, that's good. That's good. And after every 3 months, there is some call for the postdoctoral fellowship, you are saying.
Maybe there is a call coming in the June now.
Okay, in June
There
itself
was
it
a
may
call in
come.
January. Yeah, there may be again call. So it happen every quarterly. We are recruiting now postdoc,
Okay,
and
that's
not only recruitment for postdoc. We will try to send them the abroad for at least 1 or 2 conference also. Okay,
good.
depend.
That
Certain things depend.
no,
Okay,
that's really good. And we at MNIT we have very close association with ISRO. At
very good.
yeah, at MNIT Jaipur, we have Regional Academic Center for Space,
I see.
which is totally funded by ISRO. And
Okay, good.
through that RACS scheme, we are supporting many minor projects. Even we are supporting the minor projects from undergraduate students to postgraduate students as well as from the PhD students. And the faculty members in the North India region, they also can submit any proposal to ISRO through RACS.
Very good.
And this will be funded by MNIT through the RACS fund.
Yes.
And yeah, that's good. And all the participants at MNIT also, we have now the position for like the fellowship for doing PhD. Even if you do not have NET or GATE, some fellowships
Yes.
are available for them also.
Okay.
So
Good. Good. That sounds
yeah,
good.
yeah, that's good, Professor Sarvesh. I'm really happy to meet you online through this FDP.
Thank you so much.
And I'm sure
Thank you
in
so much.
future I'll be able to invite you at Jaipur also in person,
Sure,
and I'll
sure.
be
We
yeah.
will
Then
do.
we can meet also, and all the participants also. We are planning to have one more FDP on the similar topic in the month of almost October to November, when the weather at
Oh,
Jaipur will be
great. That
comfortable.
will be interesting. Yeah.
Yeah, and that time I would like to call all the speakers and all the participants in person in the physical mode at Jaipur. So
Sure.
yeah, that will be nice too, because this time the Jaipur weather is so warm. I mean, so high temperature. It's not advisable to do the offline program here. Yes, Dr. Satyendra Prasad ji. Yes, we will be having one more FDP, and that will be in hybrid mode. But obviously, all the speakers and those participants who would like to come in person, they will be giving the chance to come to Jaipur and to attend in person. Yeah, so now with this, I can now conclude this session. And this session, we today in the morning we had the lecture by Professor Sarvesh and by Professor Manoj Thakur, as well as one lecture was delivered by Professor Ashish Avasthi from NIT Calicut. And in the afternoon session, we have heard two very interesting lectures by Professor Sarvesh Kumar. And Professor Kumar, whenever you are free, please send me your slides in the PDF
Sure,
format.
sure. I'll do it right
Yeah,
now.
yeah, so that by tonight itself, I can upload on the Canvas platform.
Sure.
Yeah, and participants, one announcement for you. I have just shared one email with all of you in which I have given a revised schedule for day 8 and day 9, means for Monday and Tuesday. There are minor changes. So you can go through that revised schedule, and accordingly you can come online to join these lectures. Okay. And participants, you will be having quizzes on last day, means on day 9, and earlier it was from 4 to 6. Now I have preponed it from 3 to 5, and at 5 we will be having the validity. So all the participants are requested to please take the part in the quiz. There will be a simple multiple choice questions, 20 questions in each quiz. Like one quiz will be for 1 hour. You have to solve all this in the online mode through the Canvas platform. And don't worry, it will be a simple questions. Those who have attended the lecture seriously, they will be able to solve these questions easily. The level of the question is from low level to mid level, but I'm sure it will not be at very high level. Okay, because you have attended an online lecture, so I do not want to go up to very high level. So with this, I close this session. Dr. Nikhil Srivastava, thank you to you, and thank you to all the
Thank you so much.
participants also.
Thank you, Dr. Nikhil. Thank you so much. Thank you.
Yeah. So bye bye. Good day. See you tomorrow.